In this video, we're going to talk about conditional probabilities. Before we define what a conditional probability is, we'll look at an example and help us see exactly what this should involve. In this example, we're talking about a total of 4,000 people, some of whom are going through a foreclosure process, some of whom are unemployed, and some are both. First, let's make a Venn diagram of what's going on in this situation. So we have two main groups out of this total. We have the unemployed. We also have the foreclosed. Now we want to take this information and put it together on a chart. In the Venn diagram video and in the book it talks about this, that the overlapping part, the and part, the intersection, here is 40. When I'm filling in the rest of the numbers, there's 50 total people who are foreclosed on. There's 10 more than the 40 who are both. When I say 50 are going through foreclosure, I mean 50 total, including these 40. There are 320 others who are unemployed. This accounts for 370 of the 4,000 people. So there should be 3,630 people left out here. All right, so that's how the numbers are going to break down in the Venn diagram. Next, we're asked to determine the probability of being in the foreclosure process, the probability of being unemployed, and the probability of being unemployed and foreclosed upon. Alright, so the probability of being foreclosed upon in this case, well, 50 out of the 4,000 people total. And I want to write this as a decimal. This is 0.0125. Alright, the unemployed was 360 out of 4,000, or 0.09. The unemployed and foreclosed upon, this was 40 out of the 4,000, 0.01. Let me be careful about this. As you read that question about the probability of being in the foreclosure process and being unemployed, I want to stress this. They were asking how many total people in this entire set of 4,000 people were both things true of. Alright, that's going to be a different question than what we're about to examine. So one more time. When I ask this probability of being unemployed and being in the foreclosure process, this is talking about the whole. The number in the sample space represents the entire set of people being considered here. Next, we're asked to determine the probability of being unemployed given that you're being foreclosed on. Alright, that given that really represents a different question. We're going to write these probabilities this way. What's the probability of being unemployed given that you're being foreclosed upon? When we're asked a question of this sort, what we're really doing is we're fundamentally changing the sample space. We're changing what it is that we're examining. Here we're working on the assumption that we know we're only dealing with the people who are in the foreclosure process. How many total people was that? That was 50. This is going to represent our denominator then. Alright. Now we're asked what's the probability of someone being unemployed given that they're in that foreclosure process. Well, there were 40 people who were unemployed in that F. So we're going to put a 40 as our numerator. Alright. So this should be the probability here, and this is 0.8. You'll notice this is a very, very, very different number than what we had over with that last question. But what we're doing when we're doing a conditional probability is we're changing what it is that we're using as our sample space. We're conditioning the probability of being unemployed upon the idea of being part of whatever the second part is. And generically, this will be how we'll structure this. This amount up here, in this example, was the number in A and B, or more broad, generally, it was the intersection part, it was the AND part. Here was U and F. Here, this denominator was the number in F. In general, that would be B, the second thing. So this is going to be our generic formula for the probability of A given B, which is on the next slide. Now, I did this in terms of numbers. Very frequently, that will be the case. This is equivalent to the probability of A and B divided by the probability of B. Typically, either the number formula or the probability formula will be easier to use, one or the other, but they are both correct. Let's look at some more examples. To reiterate, we're going to say that the probability of event A occurring, given that an event B occurred, is given by the probability of A and B divided by the probability of B, which is also equal to the number of A and B in A and B divided by the number of B, depending on which set of information we have. So for instance, in example 2, we have a table with some information on it, and we're asked to find the probability that the service was poor, given that the meal was dinner. Poor service, given that the meal was dinner. So here in the table they have some numbers. So we're going to find the number of times that the service was poor and dinner. Now, sometimes you have to kind of interpret what that means, but that's going to say that the service was poor and the meal was dinner. It's both of those things occurring. We're going to divide this by the number of times dinner was served or surveyed. Now these numbers should both be in the table. If I look on that, I should see the service was poor at dinner 28 times, and that dinner was the meal evaluated a total of 38 times. And that should be the answer to example 2. I want to simplify that or write that as a decimal, but that's what we're looking at for conditional probability. Extending our idea of what exactly this amount means, let's look back at a Venn diagram. And to make this a little more clear, I'm going to use different variables. Let's use C and D, and let's suppose, that's a Venn diagram, this is a tree diagram. We know the probabilities of this, so I'm going to make a probability tree. And they're related to two other events, E and F, whose likelihoods are 2/5, 3/5 in this branching, and they're different over here at 6/7 and 1/7. Now, one thing you want to notice about this is that the way we're thinking about this, we can use this equation to actually solve this for the probability of A given B, the probability of A and B. The way I have that written there, well, I can multiply this denominator of the probability of B times both sides, and I would get the probability of B times the probability of A given B. So the probability of A and B can be written as the probability of B times the probability of A given B. I'm not going to write this out on the board, but if you switch these letters, it switches the B and the A, and it switches this to an A. In that resulting equation, if I work that out, you would see that the probability of A times the probability of B given A also gives us the probability of A and B. This is going to allow us to answer questions like this. Let's suppose we were asked the question, what's the probability of F given C? Well, what that's saying is, what's the likelihood of F happening if we know that C happened? So here we're saying, the way I drew this tree, first C happened, then F happened. This is something I can just read off of the chart. Well, let's suppose we wanted to know the probability that both F and C happened, or I could write it either way. C and F happened. Well, I have two choices here. I can either use this top formulation or this bottom formulation. I know how to find the probability of F given C, that's 3/5. So I'm going to want to write it as the probability of C times the probability of F given C. That is, you'll want to be careful in how you write these, because sometimes you'll only know one number or the other. Looking at this chart here, the probability of C, that's 1/4. The probability of F given C is 3/5. Alright, so multiplying those out, we'll get this as 3/20, or 0.15 as our probability. There are several other probabilities you could get off of a chart like this. This is what we're going to be concerned with right now, and we'll go on to show some examples of how to use that next. In example 3, you're told a hat contains 3 bills, a $1, $5, and $20 bill. 2 bills are to be selected at random with replacement. Let's find the probability that both bills are $20 if at least one of the selected bills is a $20 bill. Well, this is another conditional probability. We're asked to find the probability that both are $20 bills given that at least one is a $20 bill. So just the probability that both of them are 20 and at least one. We'll talk about that in a minute. Divided by the probability that at least one is a $20 bill. So we need to find a way to answer both of those questions. There's a variety of different ways that you might want to do that. But what we're going to look at is the underlying experiment in this problem. So again, we're told 2 bills are to be selected at random with replacement. So let's look at the possibilities of what we can have with this. There's a couple different ways you can get to this result, but one of the most straightforward is to recognize, to draw this out with the tree diagram. You have a $1 bill, a $5 bill, and a $20 bill. After you select the first, you put it back. I can just draw this tree diagram out. With the outcomes, so these are the possible outcomes. I can have a $1 bill, $1 bill, $1.05, $1.20, $5.1, $5.5, $5.20, $21, $25, $20.20. What you're going to see here is there's 9 total outcomes. So the probability of getting at least one of those 9 to be 20, well, let's go through and list them. Turns out there's 1, 2, 3, 4, 5 different ways to do this out of the total of 9 different things. Now, the other question, that probably they're both 20 and at least one of them is 20. This is an interesting question because it gets to something that you don't see a whole lot often. But at least both of them being $20 bills includes all of the ones that are at least 1. So these are, if I drew again Venn diagram, both is completely contained within the at least 1. But we're going to see here that this example here, where they're both 20, is where they're both 20 and at least one of them is 20. That's one of the 9 ways. So the overall question we were considering should be, well, they're both in at least one of the 9 ways. 1 divided by 9, divided by 5 ninths, multiplied by the reciprocal. We'll see that the probability of this outcome is 1 out of 5. You'll notice the way that I drew this out with blocks, the blue 1 divided by the 5 total blocks gave me the same result, and that would, generally speaking, be the case. So probably that they're both $20 bills, given that at least one of them was 20, was 1 out of these 5 ways in which they were both at least 20. And that's kind of the idea we want to get at with the conditional probability.